The first thing that we do today is going to be more local linearization examples. The formula, again, is that f of x is approximately f of a plus f prime of a times x minus a. This is called local linearization. It's actually got other names. It's also called tangent line approximation. You're finding the equation of the tangent line to the original function at some specified point A, and then you're trying to use it to do a linear approximation is another name for it. We could give this function that you see on the right a name. Oh, how about L of x? L standing for linear. It is a linear function of x. Again, the hardest thing about this subject for people seems to be, based on my experience, that they just don't understand the role that, for example, A plays in this formula. A is a constant. You have to plug in whatever given value of A that you have. Now, that doesn't mean the problem is phrased in terms of A equals something. You have to understand the phrasing of problems. Like number 1 here, it says find the tangent line approximation for square root of 1 plus x near x equals 0. So the function f of x is the square root of 1 plus x. And the value that x is near is the value of a. Now, it seems kind of funny. You're saying x equals 0 here, but you're really thinking about just values of x close to 0 when you do the approximation. But saying x equals 0 specifies what a is. So in this problem, a is 0. Let's go ahead and write down what we know for this problem. F of x is the square root of 1 plus x. Same thing as 1 plus x to the 1/2 power for the purpose of taking a derivative. The a is what x is said to be near. That's 0, even though you don't see an a in the problem statement. It's understood that that 0 is the a. Now just use this formula. We have to plug in 0 into f, and we also have to plug in 0 into f prime. So we have to find f prime. Find the derivative of 1 plus x to the 1/2 power. Bring down that 1/2. I'm using the chain rule here. Plug in the inside function, subtract 1. 1/2 minus 1 is negative 1/2. Then don't forget to multiply times the derivative of the inside function, 1 plus x, though that is trivial in this case, it's times 1. The derivative of 1 plus x is 1. So because of that, you wouldn't actually have to write times 1. Plug in a. A equals 0. What is f of 0? It's the square root of 1 plus 0, which is the square root of 1, which is 1. And what is f prime of 0? It's 1/2 times 1 plus 0 to the negative 1/2. Yes, times 1, but I'm not going to bother writing it anymore. 1 to the negative 1/2 is 1. 1/2 times 1 is 1/2. This is a 1/2. Therefore, the tangent line approximation for this function near x equals 0, you could write as an approximate equation, f of x, which is the square root of 1 plus x, is approximately, I'll go ahead and write the abstract form here first, f of 0 plus f prime of 0 times x minus 0. I'm just using that general formula at the top right here for this situation with a equal to 0. Now simplify. F of 0 is 1. F prime of 0 is 1/2. X minus 0 is just x. There you go. That's the answer. That's the tangent line approximation to this function near x equals 0. You could also call it a local linearization. You could also call it a linear approximation. There's lots of names for it. What is going on here? If you think about it graphically, the function square root of 1 plus x has a graph that looks the same as the square root function, except shifted to the left by 1 unit. If you imagine plugging negative 1 in for x, for example, you get 1 plus negative 1 is 0. Square root of 0 is 0. When x is negative 1, y is 0. That point is on the graph. What does the graph of the square root function look like? It's increasing in concave down. It looks about like this. This is f of x equals square root of 1 plus x. F of 0 we found is 1, so the second coordinate of this point is 1. Its coordinates overall are 0, 1. And we also found that the slope of the tangent line to the curve at this point is 1/2. The tangent line right there has a slope equal to 1/2. And you can see visually, the tangent line looks like it's a good approximation to the curve. That's what differential calculus is really all about, is approximating curves with straight lines. This linear approximation stuff, though it might feel unnecessary because we have technology, is actually getting at the essence of what differential calculus is about. Approximating curves, locally speaking, near points with straight lines. Because when you zoom in close to curves that are smooth near any point, they will look more and more like straight lines. That's why. The closer you zoom into the red curve near this point, the closer it's going to look like the green line. The tangent line is the best linear approximation to this curve at that point. We could, you're not asked to do this, but we could use this to, for example, approximate a square root. We could use it to, for example, approximate square root of, oh, say, 1.3. Why? Because 1.3 is the same as 1 plus 0.3. Since the function is square root of 1 plus x, this is the same as f of 0.3. And by this approximate equation up here, this is approximately 1 plus 1/2 times 0.3. That's something you can do in your head. Half of 0.3 is 0.15. So our approximation is 1.15. Is that going to be too big or too small for the square root of 1.3, and why? I'll also explain why.
Big because f double prime of f(x) is always decreasing.
Close, it's negative.
Sorry.
Yep. So what he's saying is f double prime of this function is always negative. The slope is decreasing. The graph is concave down. And you can see because of that, that the tangent line is above the curve. This is a second coordinate of a point on the tangent line when the first coordinate is 0.3. I can try to draw it here, but it's a little difficult. That point that I just drew in green on that green line has coordinates 0.3, 1.15. It's a bit above the red curve. So f of 0.3 is a little smaller. What is f of 0.3? It's the square root of 1.3. Yes, it's a little smaller, about 1.14. The error in this approximation is also something important to know about. What is error in approximations? Call it approximation error. It is the actual value minus the approximate value from the approximation. I'm calling this approximation error. The exact approximation error is the exact square root of 1.3, which is an infinitesimal that goes on forever and ever without a repeating pattern. Nobody knows all the digits. Minus this approximation that we got, 1.15. To figure out approximately what this approximate error is, we need technology. Square root of 1.3 is approximately that. Subtract 1.15, we get a small negative error. Negative 0.0098246, say. Or in scientific notation, that would be negative 9.8246 times 10 to the negative, what would it be? Move the decimal to the right 3 spots there to get it to be to the right of a 9. On the order of close to 10 to the negative 2, close to 0.01 in absolute value. Question?
Why the negative is like why
Because this number is smaller than this one.
no,
try it with-
the scientific notation. You got 2 negative values.
I only have a negative right there. This is a separate line. Yeah. Negative 9.8246 times 10 to the negative 3, which is close to 10 to the negative 2. The approximate value is smaller than the approximation we got from the local linearization, and so the difference is negative. And it is a good thing in general to keep track of when errors are positive or negative. I always remember this equation by the fact that actual comes before approximation in alphabetical order in a dictionary, say, if you're a page through a real life dictionary, comes before, AC comes before AP. That's the way I remember the order. So what this means is that the approximation is too big, the error is negative, and if the approximation is too small, the error is positive, which seems a little counterintuitive, but that is the official way to do it. Let's do another example. Let's skip number 2. Let's go to number 3. And maybe we'll also try number 6. Number 3 says, find the tangent line approximation to 1 over x near x equals 1. Notice also some of these questions are say, find the local linearization. It means do the same thing. Do what we just did. So the function now is 1 over x, and the a is now 1 instead of 0. A equals 0 is the most common value of a to use, but it's not the only value of a we can use. We can use other values of a. Okay, so the function in the new example here is f of x equals 1 over x, which is the same as x to the negative 1 power, and the a is 1, not 0. It can't be 0 here, right? Because we'd be dividing by 0. The function's undefined when x is 0. What am I going to need? I'm going to need the derivative, f prime of x. I could use the quotient rule, but I don't have to. I could just, it's simpler to use the power rule. Negative x to the negative 2. Same as negative 1 over x squared if you prefer. I need to plug in a equals 1 into these things. F of 1 is 1 over 1 is 1. And f prime of 1 is negative 1 over 1 squared is negative 1. So the local linearization for this function f of x, which is 1 over x, I use the same formula as before, but now a is 1. And again, I could call it L of x. I didn't in the last example. To emphasize, I'm using a linear function to approximate a nonlinear function. It's f of 1 plus f prime of 1 times x minus 1. F of 1 is 1, f prime of 1 is negative 1. I get that. Should I distribute the minus 1 through the parentheses? There's not a problem with that. And then I could convert it to slope-intercept form. However, for approximation purposes, it's better to leave it like this, although I'll write it like this now. I mean, with this case, it's not really a big deal one way or the other. But in general, it's better to leave it in this form for approximation purposes when x is close to 1, because if x is close to 1, then x minus 1 will be close to 0, and it would be a calculation you can do in your head. And that includes more complicated examples. Maybe where the derivative is a fraction or something, like it was in the last example. That is the local linearization. And okay, just for the sake of completion, it does happen to equal negative x plus 2, right? 1, 2 minuses there make a plus when I distribute the minus sign through. 1 plus 1 is 2. What's going on in this example? Graphically. So let's use the calculator this time to see it. So on my y equals screen, I'll plot 1 over x. I also plot the simplified form, say negative x plus 2. I want to make my window near x equals 1. Maybe from 0 to 2. How big should y be? Well, technically as x goes to 0, 1 over x goes to infinity. There's a vertical asymptote at x equals 0. The y-axis is a vertical asymptote for the graph. So technically it gets arbitrarily high, but I don't really want to make my y values go too high, just for the sake of seeing a nice picture. I'll go 0 to 2 for y as well. So the first graph we'll see is the curve 1 over x. There it is. And the second graph is the tangent line at x equals 1. You can see it looks like it's tangent to the curve. If we zoom in, could use Z-box, I'll do a zoom in. So it zoomed in closer. You're now closer to the 0.11. You can see the tangent line is looking more and more like a better and better approximation of the curve. If I zoom in again, there's the curve, there's the tangent line. You can hardly tell the difference anymore. That's local linearity. That's differentiability. Remember that word in chapter 2? Differentiable means the derivative exists. The curve looks more and more like a straight line the closer and closer you zoom in. You zoom in far enough, you can't tell the difference between the curve and the tangent line. They are still technically different, but you're so close and they're so close together that you can't tell the difference. Maybe I should try that. I'll zoom in one more time and probably won't be able to tell the difference. There's the curve technically. I just barely saw a tiny difference in the upper left corner. But they look the same. Okay, one more. There's the curve and the tangent line. You're not seeing anything different. What is this window? Okay, x is going between 0.996 and 1.004. So we're within 0.004 of x equals 1 there. We're pretty close. That's far enough so that they look identical on the graphing calculator at least. Okay. One more example. Number 6. Function's a bit more complicated. X times sine of x. Actually, this one's going to be kind of interesting. I think something weird's going to happen here. Let's do it anyway. It's a good conceptual point to see this happen. So f of x is x times sine of x. The a was 0. We need f prime, and f is a product, so we need the product rule. Got a left function and a right function. Left d right will be x times cos x. That's the first function times the derivative of the second, plus right d left will be 1 times sine x. Sine x is the right function, 1 is d left. It's the derivative of x. We need to plug in a equals 0 into these. F of 0 is 0 sine 0, that's 0. F prime of a, f prime of 0 is 0 cos 1 plus sine 0. Oops, not cos 1, cos 0. I was thinking 1 because cosine of 0 is 1. But 0 times 1 is 0. In the end, this is 0 as well. Therefore, the local linearization is 0 plus 0 times x. If you want to call it L of x is 0 plus 0 times x, which is 0. The local linearization is a constant function, 0. Why'd that happen? Well, it's because f of 0 and f prime of 0 are both 0. Graphically, if you graph x times sine of x near 0, it's going to look like this. It's going to go through the point 0, 0. And it's also going to have a slope of 0. It's going to look like a parabola near there. We can check this in a second. So the best tangent line approximation at that point is a horizontal line through the origin, in fact. If I plot x sine x, thank you, x sine x near 0, say negative 0.5 to positive 0.5, close to 0, it's going to look like sort of like your standard parabola. X squared, it's not technically x squared itself, but that's the way it's going to look. Actually, it would look similar to x squared. I'm wrong. Here it is. Yeah, the tangent line at the origin is horizontal. The constant function 0 is the best linear approximation at the origin. Yeah, and actually, if you graphed x squared as well, x squared would be a nonlinear graph, technically a parabola, that does turn out to be the best quadratic approximation to this function at 0. On this window, you can't tell the difference hardly. You can see a slight difference. Let me do a bigger window. There's x times sine x. And here's x squared. You can go beyond linear approximations. You can do quadratic approximations to functions. Is it useful? How do you think calculators and computers are programmed to do sines and cosines? How do you make a circuit compute a sine or a cosine or e to the x? How in the world would you do such things? It's a bunch of zeros and ones. Well, this is part of the answer. It's not the complete story, but these ideas are part of the answer. You can make circuits, electronic circuits, that add and therefore also subtract and multiply and divide fairly easily. Maybe some of you have even done that if you're an electrical engineering major. And linearization and quadratic approximation as well only involves those arithmetic operations: addition, subtraction, multiplication, and division. We are approximating something involving the sine function with something involving arithmetic. I'm not saying it's easy, but relatively easy in the big picture to make technology do arithmetic. It's not the full picture, but it's part of the picture. These are the most basic kinds of problems to be able to do. You did have a problem or two that was harder. Okay, 38 is definitely a harder problem, though I think I had an example in the video. Writing little g for the acceleration due to gravity and period t of a pendulum of length L, we've got this equation. Okay. Now, keep in mind here, you've always thought of little g as a constant, right? 9.8 meters per second squared, acceleration due to gravity. Technically speaking, if you want to be extra picky about it, it's actually not constant. Do you know that? If you go to the top of Mount Everest and drop a ball, it'll accelerate slower than if you're at sea level. What's the acceleration at the top of Mount Everest? I don't happen to know it off the top of my head. Maybe 9.6 meters per second squared. I don't know. It is slightly slower acceleration. G is actually not constant. There's also the fact that if you're on the moon instead of the Earth, G is a lot smaller because the mass of the moon is a lot lower. Okay, so you can think of G as a variable in here. That's not what we're doing. We're thinking of L as the variable, the length of a pendulum. What's a pendulum? It's something that swings back and forth, like a grandfather clock or something. It's got a period where you go back and forth. How long does it take to go back and forth one time? That's the period. That period depends on the length according to this equation. Okay. Actually, if I recall correctly, I think this equation is not perfect. It's an approximation itself, I believe. It's pretty good for small amplitude. Yeah, I'm sure that's right. It's a pretty good approximation when your amplitude of your swinging is small. If the amplitude's large, if the pendulum can go up high above the pivot point, the period is not this equation. It can get bigger because it slows down as it nears the top before it comes back down again. So, well, what we are doing, they didn't use function notation in this problem, but they could have. I'm going to go ahead and for sake of relating it to function notation, I'm going to use function notation. F of something. F of what's the variable? I'll call it L. So that's a cursive L, like that I like making that way instead of the way you see in the textbook there. 2 pi times the square root of L over G. We are going to differentiate this function of L. I am thinking of G as fixed, so pretending we're at sea level. It'll be helpful to do that, to rewrite it like this. Why can I do that? Well, for one thing, the square root of L over G can be written as the square root of L divided by the square root of G. That is a property of square roots. And then the square root of L is the same as L over 1/2. That's a bit more convenient for the purpose of differentiation. And for extra emphasis, I will also use both Leibniz notation and prime notation. The derivative can be written as dt dl. When you use Leibniz notation like that, as Leibniz did, that sort of emphasizes the derivative as a rate of change. How fast is t changing as L changes? And it's a little funny because for a fixed pendulum, L doesn't change. You would think about this if you imagine changing the pendulum, changing the length of the string it's attached to, or the rod. Maybe you make it slightly longer. You do a new experiment, calculate the new period. This is telling you how fast that period changes as L changes. The derivative notation can be used as well, f prime of L. The Leibniz notation emphasizes the derivative as a rate of change. The prime notation, well, yes, the derivative is still a rate of change, but it kind of just emphasizes that you can figure out the derivative from the original function. That's what prime notation kind of emphasizes. It's something you do. We find f prime when we're given f. Anyway, as far as doing it here, you treat the g as a constant, so you just leave that constant there. You've got 2 pi over square root of g, and then differentiate L to the 1/2, L being the variable. So just bring down the 1/2 and subtract 1 from the exponent. This can be simplified a bit, cancel the 2's. So this simplifies to pi over square root of g times L to the negative 1/2. If I like, I also can write that as pi over square root of g times L. That's a property of square roots. And also negative 1/2 exponents means 1 over L to the positive 1/2. All right, so that's the derivative with respect to L, but how do we solve the problem? Part A says, show that if the pendulum length changes by delta L, then the change in period delta t is given by this approximation. Before we do the details here, it would be good to rewrite the local linearization approximate equation in a new way. So back 20 minutes ago, we wrote f of x is approximately f of a plus f prime of a times x minus a. If you subtract f of a from both sides, that approximate equation is equivalent to this approximate equation. F of x minus f of a is approximately f prime of a times x minus a. And guess what? That's often called delta y, and this is often called delta x. So this can also be written as delta y is approximately f prime of a times delta x, or if you use Leibniz notation, delta y is approximately dy dx times delta x. It's almost as if you can cancel the dx with the delta x and say delta y is approximately dy. Almost can be thought of that way. I mean, I will tell you, scientists and engineers think of it that way commonly. It's not technically correct, but intuitively, they imagine doing it. Don't literally do the cancellation though. Leave it like this. So in the context of our problem, the variables are not x and y, they're L and T. In the context of our problem, we would write this as delta T is approximately dt dl times delta L. And that's starting to look similar to what you see in this problem. I guess the implication of the problem is dt dl can be written as T over 2L. That must be the implication. But wait a minute, is that right? I thought dt dl was that. That doesn't look the same. It is the same if you replace T with its dependence on L. That's the trick. If you look at this expression in this problem, T over 2L times delta L, I'm looking down near the bottom here, right there where the cursor is. And you replace T with what it equals. T equals 2 pi times square root of L over G. Let me go ahead and do that replacement. 2 pi times square root of L over G. And if you simplify this thing in front of the delta L should simplify, if I haven't made a mistake, to what we got for the derivative before. Let's see if it does. Simplify this, the 2's cancel. The pi stays up there. Let me just be extra careful here with making sure I don't make a mistake in my simplification. Square root of L over G is the same as L to the 1/2 over G to the 1/2. And I'm dividing that all by L. When I'm dividing by a fraction in the top, the thing in the bottom there can go to the very bottom of the bigger fraction. So I can also write this as pi times L to the 1/2 over L times G to the 1/2 times delta L. Continuing to simplify, I can subtract exponents. 1/2 minus 1 is negative 1/2. I can write this as pi times L to the negative 1/2 over G to the positive 1/2 times delta L. And guess what? This thing right there is the derivative we got earlier. Look, take a look at it. Pi L to the negative 1/2 over G to the positive 1/2. That is the same as this. Seems like magic, but we did get it. It's not magic, it's just tricky. Part B says if the length of the pendulum increases by 2%, by what percent does the period change? It's helpful to take this approximate equation and rewrite it in yet another way. So we've just derived in part A that delta T, the change in the period of the pendulum, is approximately that. The period itself over 2 times the length of the pendulum times the change in the length of the pendulum. Again, for a given pendulum, its length wouldn't change. When you imagine applying this, you're imagining changing what pendulum you're working with, making it a little longer or something. For the purpose of doing part B, it's good to divide both sides of this equation by T, like this, and also rewrite the right side as 1/2 times delta L over L. And it's an approximate equation. And the thing that helps you finish part B here is to understand that these fractions really could be thought of as percent changes. Why? Well, let's think about a numerical example. If the length of the pendulum changes from 10 centimeters to, say, 10.5 centimeters, by what percent did the pendulum length increase? 0.5 divided by 10, right? Which is 5%. The percent change is the change in the length of the pendulum, 0.5, 10.5 minus 10, divided by the original length, 10. 0.5 divided by 10, which is 0.05 as a decimal, as a percentage, that's 5%. Again, percent just means per 100. I think I've mentioned that before. So when you say 5% equals 0.05, it's because percent means per 100. It's just a shorthand symbol. It means 5 over 100, which is 0.05. Notice this fraction matches this fraction. It's the change in the length of the pendulum divided by the original length. L represents the original length. This kind of reasoning comes up all the time in science classes, physics, engineering, chemistry, sometimes even biology. This kind of reasoning comes up all the time. Maybe you've experienced it. You see these kinds of equations all over physics books, for example. So what do we conclude here? Again, the problem says if the pendulum length increases by 2%, by what percent does the period change? In other words, we're saying this fraction is 0.02. Delta L over L being 0.02 means, according to this approximate equation, that delta T over T, the percent change in the period, is approximately 1/2 times 0.02, 0.01 or 1%. If a pendulum length of the rod gets longer by 2%, the period should increase by 1%. That's what this means. A 2% longer pendulum makes the period 1% longer, meaning that the oscillation is slightly slower to make the period 1% longer. If the original period was 2 seconds, the new period would be 2.02 seconds, 1% greater than 2. Right? Again, this kind of reasoning comes up all the time in science and engineering classes.